Standard materials and structures, where we don't talk and we come here to work. Right though. So we are starting with module 3. I hope you went over module 2. Module 2 is really not a bad module. Module 3, there's a lot of talk. People say it's difficult, but it's not. I'll make it as easy as possible. So just you must make sure you follow me. But let's begin. Right. So I obviously like people to send me questions on the Wednesday, but you guys are writing and you're going to work through it today. So I'm just keeping the same structure as we had before, even though we have the 1 hour or just over the 1 hour. But what's happening with this chapter? So guys, I mentioned to you before, right? We have, in terms of the mechanical loading, right? Okay. We have a tensile load, a compressive load, a shear load, a torsion load, and a bending load. These are the 5 fundamental mechanical loads which most mechanical structures experience, right? But on the side, we also have the secondary loading, right? One is due to temperature, another one is due to pressure. And we're particularly talking about hydraulic pressure, pressure in pipes, tubing, refrigerants, in pressure vessels. So, but today's focus, right? We are focusing just here. So what happens when a change in temperature happens to particularly a solid, in this case, a steel, right? So I hope I'm giving the context here. Now, I want us to be really clear. What are we doing today? And I'm giving a good overview so that you're able to understand what's going on. We're going to be looking at series arrangements, right? And parallel arrangements, just as before. But, spelling parallel wrong. But what you must be cautious of, is that the first thing is, right? We look at the stress due to temperature. Okay? That's the first thing. So, the stress due to temperature has its own, not its own set of rules, it's nearly similar, right? But let me say its own set of rules, right? These rules will be explained in these paragraphs over here, which I'm going to show you. No? So that's very important. Make sure you understand that within your textbook. I hope I'm clear, colleagues. So this has its own rules, right? Okay. And then we're also going to include the stuff we did in module 2, right? Which is stress due to the mechanical loading, right? Mech loading. And what I mean by that loading is typically a tensile and a compressive load. Colleagues, are you with me? Do you mean yes or no or thumbs up?
Yes, sir, we are with you.
100%. So that's the key thing. And I want to just show you one example how it's structured, right? So you must not confuse the two. Okay. It's very important. Now, the last thing I want to say here, right? And number 3, what they ask for is resultant stresses. Okay. So in the resultant stress part in the question, you are adding stresses in 1 and 2. So whatever stress you add here, you're adding whether it's positive or negative. This is basically the whole chapter, a big overview. Okay. I'm assuming everyone gets that. And what I mean, I'm going to give you a simple question, what it looks like before I solve it. I'm not going to solve it now. I'm going to first warm up and get here. So in this case, here we have a compound shaft, a steel inside a copper tube, right? Something like this. Okay. And the first question, if you look at it, right? So I want you to understand the pattern. They ask for the change in temperature, right? Here in this question, we're going to find stresses, right? With a tensile or compressive. Right, students? The next one, we're going to find due to the mechanical loading. So these are the laws you can apply in module 2. Then you get the mechanical part, and then what you do, you basically, the resultant is going to be a sum of the plus or minus of the temperature and the mechanical. Am I clear? Can you see the pattern? Colleagues, I hope you see the pattern. Welcome, Hussein. I'll say that again, right? Good evening. Yeah, sorry. The first part of these questions, typically, we look at the stress due to the temperature. The second part, we look at the stress due to the mechanical loading. And in the last part, basically, we're adding the stresses due to them both, whether it be positive or negative. Are we on the same page now? That's the overview of this chapter. Okay. Are we happy?
Yes, sir.
100%. Everyone else?
Yes, sir, we are winning.
Okay, good. That's very important. So that's the overview, and now we're going to start breaking it down to the specifics now. So we'll start solving problems as normal. Obviously, I'm adjusting my style, because yeah, in no time. But anyway, let's not talk about time. Let's get to the business. Okay. I want to come here. We'll start with this. So we're still looking at series and parallel, right? It's still there, but the difference is now the two relationships. If you remember, you have one for force and one for change in length. This one here, this is for the temperature condition. Your force remains the same, right? Yeah, you can ask me again why, but for now, just know that it remains the same, right? It experiences the same force when it's going under the temperature change, right? The next thing you must know, which is the change in length one, right? Remember, we have a force and change in length. It's this one here. You see that? So this is only for the temperature side, right? For the series arrangement. When you come to the mechanical side, you have to go back to module 2's formulas. I hope I'm being clear. So these are the formulas you'll be using today. Okay. Again, what the chapter is about, students, it's quite simple. It's basically when we have a change in temp, when we have an increase in temperature, steel, that solid will exhibit a stress in it, right? It's a very small stress, but when you increase the temperature, it will change the length. If you change the length, you get a strain, therefore you get a stress. Okay, so that's the idea over here. So this is only for the series arrangement, right? Okay, but we're gonna come back to this again. For the parallel. All right, so let's begin. So this is my first setup. So figure 3.16, get your books, pens, calculators ready. Shows a compound bar that fits snugly between the rigid end supports, right? The key is rigid end supports, right? It must be fixed. Just remember that. The left-hand side is made of steel. The right-hand side is made of brass. Does this happen in real life? I highly doubt it. If we get an increase in temperature of 65, now we must calculate, right? The stress in the steel and the brass due to the temperature, and in the final distance of AB from the right hand support. Hopefully we can do left hand as well. So the point here is with the assembly, let's say it's in a furnace, let's say we're in the mines or wherever we are, and there's an increase of 65 degrees of this assembly. We want to see what stress this arrangement is done due to the temperature, right? So we go to these rules. Here we begin. So the first thing we do, 10.1, we must find the relationship between the two. And I want you guys to work with me, right? Remember what force is equal to? Let me call it steel and brass, my students. So it's steel and brass. So we have steel, right? And it has an area of pi over 430 squared, right? And the first step here, we want to find, what is this guy now? We want to find a ratio between the force of steel and the force of, the stress of steel and the stress of brass. Okay, so brass is a 14 mole. Students, can you please quickly hit me with the ratio between stress, the two stresses? Yeah, okay. So again, area, power 4 d squared, that's 30 mole, and that's a 14 mole. So let's get the ratios quickly. And if you're unsure, please stop me. For me to be slow, I can be slow, but yeah, we won't be able to solve enough questions during the time. So yeah, so just let me know. If you're unsure, please stop me.
1,778.
Can we please confirm that? We can't trust everyone here. We engineers, yeah. We check, we validate.
100%.
Yes. Okay, gents, I believe you all gents here. 1.778.
Yes, I also got that.
100%. So if we do that, typically you're going to get some marks just there, right? Okay. Once we have that, right, all we must do now, right, is basically come into this formula over here. So now this formula, they typically find you can do the force way or the stress way. I'm just doing the stress way. So what this formula looks like, the FL, so remind you guys, extension equals, so let me write it better here. Okay. So the total extension, all right, is equal to well, let me write it like this rather. It's going to be stress change in length 1 plus change in length 2 equals x1 x2. What is happening, students? Let me explain to you so that you understand. In this arrangement, right? We increase the temperature, things are going to start happening, right? We're going to find that both these guys are expanding, right? So if this expands here, right, that goes that way. That goes that way, right? This is the understanding part. This goes this way. This goes this way. Do you agree with me, Newton's third law, that this arrow is going this way? Right?
Yes, sir.
This arrow is going that way. Okay? So what you are seeing, right, macroscopically here and here, that guy is being compressed, right?
Mm.
Similarly over here, this guy is also being compressed. Think about it, right? They're both pushing each other. You see? Okay, very important part. By that virtue, right, due to the temperature increase, both of them are going to experience a compressive stress. Are you with me? Not a tensile stress. So Mila, you want to say something? Or Hossein?
No, sir.
Yeah, I mean, you know, doing for sake of engagement. So this is very important for understanding purposes, right? Okay. So now we get an increase in temperature, but in the same time, because we restricted, there will be a mechanical element in it, and that's where the change in length comes in now, right? So don't get confused. We're just dealing with temperature now, but let me not mention those things now. So now we come back here. So this part of it is basically okay, let me just write it out for you. So this is the formula will look like this. It's over here. This is essentially due to the temperature here. Okay, so stress L. By the way, this is the coefficient of expansion. I believe you guys might know it. L1 plus alpha 2, and in time the same temperature differential. Thank you. Over here, we have FLEA, this one, if you remember. But I'm going to put it in the stress way, just to make things easy for us, because we're grown up. We know that force over area gives you stress, L divided by E. Okay. So I'm going to use this one instead. Why? Because we already have it in stress ratios. You could have found the force ratios, and then find the forces, and then divide by the areas, but I'm just going straight to the stress. I hope I'm being clear there, right? We know there's two approaches on how to do this. So in this case, I'm going to have stress steel, L over E, steel, obviously. Plus I have my brass L over E. Okay, so we know it's both brass here. So again, guys, you could have done the force approach or the stress approach. I can do both if you want. But this is what it is. Okay, so that alpha is basically called the coefficient of linear expansion, and it tells you how that they also differ from material to material. So we have steel, which is 11. And brass, which is 17, right? The all times 10 to the power negative 6. So 1 is 11 times 10 to the power negative 6. This is my steel. I'm going to just call it, just forgive me for my notation. And that cow is 125 more, right? So 0.125. We add him as well. And what is it now? And the other guy is 17 times 10 to the negative 16, right? Okay. I'll give you a moment to catch up now, and we times it by each respective length, and that length is 200 more. Okay, so it's 0.2. Then I'm gonna immediately go to this. We already have the stress of steel, so we take this guy, this bad boy, and we substitute him in here, right? So we know that that's going to be stress of brass times 0. It's under 0. That's going to be 1.778 times by each respective length, which is 125 mole, divided by each respective each respective elastic moduli, which is 200 times to the power 9. Plus we take brass, we're keeping the same, that'll be our only unknown. We times by each respective length of 0.2 and we divide by each respective elastic module. Right? Are we happy with that? So can you see your unknowns only? Brass, right? And you solve for brass now. Oh yes.
You forgot
Don't
the
forget the
temperature.
times
There's a
temperature 100% 65. Okay. Is there any questions? You have to solve the stresses for me. That is why Hossein, get ready. Right though. When you're ready, just tell me the answer, then we can move on.
you want a complete answer or just one first on the left, then on the right?
You can give me the complete answer for brass.
Okay.
Or if you guys want each step, it's fine. I mean, it depends.
Mm.
I'm just looking for this really. Yeah, because I know the maths we all can do, I believe. If not, just please tell me so I can actually do it step by step. All right, I'll give you guys 3 minutes for that.
I got, don't know if anybody want to confirm, but I got 99,759, what's it, megapascals.
Yeah, 99,759.
759.
Louis, can I have my cents, please? Tensile compressor.
Yeah, that's right.
It will be compressive.
100%. Very important, right? So we just times that guy by the what you call it? The 1.7 something.
Good.
What do we get there?
177,371.
371. Okay. MPa. Also compressor, right?
That's correct, yes.
Okay. Well done. So guys, this is only the temperature part, right? And we're gonna do what parallel you're gonna see nicely. I hope there's no questions over here. So now let's do the next one. It says the final distance of AB from the right hand support, right? So we're looking at this particular support. What they try to see, students, is how much this actually kind of extended by, right? It's a really vague thing, but this is the way we're gonna do it. Okay, so I'm gonna say that I don't know how to call it here, right? The book just calls it AB. I'm gonna just go there nomenclature, right? I don't know. I normally write length. You know, length or like length AB, whatever. Okay. So analyzing this, we want to see how much it actually moved, right? So how this works, right, is that we take the original length, then we must add something, and then we must subtract something, right? So let me analyze this bar for you just here quickly. So the bar's over here, and obviously we obviously know there's another bar here. So we have a length, right? That's the original length, right? Length O, LO, L subscript O. We increase the temperature. This guy starts to increase a bit. Obviously, under constrained conditions, we get a change in L. You guys agree with me? You guys agree? So we have a length, we apply temperature, it increases in length, right?
Yes.
Yes, right? Then the next step, what happens now is that when it's increasing, because it's fixed over here, right? It gets compressed, which we mentioned earlier on. So now we must throw in a negative a mechanical extension. Can you see what I'm saying to you? So here is original length plus the alpha L, the alpha L change in T. This is obviously of that element minus the stress in brass L over E. So this is the temperature increase. This is the mechanical decrease because of the fixed end. So in this case, that's going to be a 0.2 plus, if you remember, this guy was, what is he again? 17 times 10 to the power that, and all these questions are basically the same. Yeah, 0.2 times 65. We've got our stress in brass. The reason why we're using brass, because we're using from the right-hand side. I'm going to ask you to do the left-hand side just now. Should come out to the same, roughly the same answer. There's a part to be exactly the same, which is this part here. So we're using brass. So we're watching extension going that way. Let me write it in the other color. We're seeing how much it grows this way relative to the other way. Let's move back. And my stress in brass is, what was it, guy, again? 99.759 MPa times about the length. The length, I believe, was 0.2 and dividing by 100. Okay. All right. And if you do this, you'll see how much it basically grew by its net value, so to say. Okay, what did we get there? I think, Louis, for this one, let's do individual. I can get, we already know this term. I want to have this term here and that term here alone.
I don't know if I'm right. I got 0.221 times 10 to the power minus 3.
This one? This one?
Yeah, for this one, yeah.
So what's it? 0?
0.221
Yeah.
times 10 to the power minus 3.
Sure. This guy?
And then the other one I got, what is it now? 0.1995.
Yes.
Times 10 to the power minus 3.
Okay. So if you add them up, what do you get? All of this?
Very little.
Yeah, it's supposed to be small. Remember, it's temperature. You don't see it. It doesn't make sense. It's a point of a mole. You don't see it. 200.0.2 something or whatever.
Yeah, I got 0.20000215. I'm not sure if it's correct.
Yeah, 0.
Yeah, 0.000 and then 215 at the end.
215, like this.
That's correct. Yes, sir.
Is it 3 zeros? Yeah, that's really in meters. So
yes,
in millimeters,
yes.
this will be 200.0. Is it 0? Another 0 here. How many zeros am I in? No, it's 215. It's supposed to be small. You don't see a lens due to temperature that big. You see what I'm saying to you? You don't see it. Okay. I hope everyone has done that. Now I want you to do from the left-hand side, but Louis, can you just quickly tell me, and I'm asking Louis deliberately because it seems like he's on fire here. Can you just sum up this 2 for me quickly? What's that minus that? I just wonder, just that value alone. That 2.
Yeah, no. Yeah, it's more or less zero. It's more or less what's in the answer: 0,0215 times 10 to the power minus 3. So it's basically
Zero,
yeah,
zero.
2. No, it's 10. Sorry, 0,0.
Yeah, 215.
215, yeah, basically times 10 to the power minus 3. So
Okay. So my point is like, I want you guys to do it from the right, eh? But what you're gonna find is that they experience basically the same kind of this part should be the same. So if you do from the right hand side, from the left hand side, right, you can obviously use now the steel. So you take the original length of the steel plus each change in length due to the temperature, right, of the steel, minus now the mechanical part of the steel. But then you're gonna find that obviously this length is smaller, but this part is the same. I don't know if I'm making sense, because I must experience the same change in length somehow, or something like that. They should extend roughly the same. Bit of a mouthful. Welcome. You can try to do that quickly. For the ones who's not sure, is there any questions? Time's running out. Is there any questions? Is there any understanding which is missing? Brandon or Shane?
So the only thing that confused me was
Yes.
the positive and the negative
Explain.
when you did this calculation now. So I used minus 2.21 to the power negative 4, and then I added the 1,995. But I see you got it the other way around. You have it the positive 0,221 and the negative 0, so I just have that the other way around.
Yeah, so again with understanding, this is what I trying to explain. I don't know the other book talks, but this is the actual way. You see, this change of temperature due to the temperature, right? So the bar extends. Are you with me?
Yeah.
The reason why this is negative, right, is because when it reaches the restriction, this causes the compressive force within the bar. Does it make sense? Think of a bar pulling. Like put your 2 fists together, right? Imagine it fixed between 2 things, and imagine it extending. You find out that your actual the front part of your arm is actually being compressed. If you think about it, as it's growing. Yeah. So that's why that's actually negative. I think the Toy did a better job explaining. Yeah. But if you get the same answer, okay. I don't wanna get into that. Maybe I don't know what I'm talking about, but who knows?
No, my answer was 199.995. So it's like off by a very minimum.
Yeah, we got the same answer, yes.
As the 200 or the 195?
199.
200.
It should be the 200. Yeah, it must be the 200. It could. The only time would be 195, right? Is if it was if it was contracting. Now I'm saying 195 because it was contracting. So now maybe there's a contraction happening within the setup now. So it's pulling. Are you with me? That's when the temperature is decreasing, not increasing now.
Yeah.
But yeah, I don't wanna get into. But are we happy with this one, students?
Yes, sir.
Yeah, so this is how it roughly goes, right? If you do a few of them, you pick up the same pattern. So I'm gonna skip question 2. I think you guys can do that. Maybe you can post the answers in the group, then I can send it. But it's coming from a paper. I'd like us to embark onto to the parallel question now, if you don't mind. So now, I wanna make sure I encapsulate all the relevant stuff here. I thought I would bring this thing work, but I still like a doesn't. It's not clear. All right, let's do parallel. Okay. So some questions, question 3, sorry, question 3. Okay, I'll paste it here. So you'll pick up the pattern, I promise you. You'll pick up the pattern. But this is the one way to ask. This is the other popular way. Right, though, here we go. So here we have a parallel setup, right? It's the one I showed you as an illustration. I want to perhaps just give me a second. I wanna go steal an image from PowerPoint quickly. And this is the one where you must pay the most attention to. I hope my battery won't die in time. I'm just making a quick tube for us here. Okay, some tube at least, something like this. I'm gonna paste it here. So the first thing I wanna make you aware, right? For temperature, right? Stresses 3.1 students, right? For parallel arrangement, these are the laws you're going to be looking at, right? So it's not the same. It looks like this. So what's the only thing what is the same? The temperature. Your forces is still the same. And that force is essentially coming through the restriction part, right? It's the same force, right? Don't get confused between the mechanical part in module 2 and this one. And over here, instead of having a plus, we have a negative. And the reason where this comes from is because the one material will expand faster than the other material. And what you're gonna find, is that the one material will experience a compressive stress, right? I think it's material 2. Whereas material 1 will actually experience a tensile stress. What that visibly looks like in our particular example is this. I want to show you an illustration like this. So this is what I'm talking about. Okay, in this case, okay, it's who's expanding fast here? It seems like it's 1. So here we have 2 materials in parallel, and the one grows faster than the other one. And what you find at the first one, I don't know what are they saying here. Because the 2 bars equivalent of force the same, the tensile force in material 1 and the higher puts. So you must just be cautious of this. But the main thing is, if you look at these formulas, this is what essentially is going on. So the N5 books make it quite easy, right? So now your force is still the same. Therefore, you still have to find a stress ratio. And then when you find the change in length, you must take off the 1 minus the 2 alphas, basically, right? The reason why L is all common here, so we just basically divide the length out. So that's why you don't need the length in this particular formula. So they are saying here, this will decrease in temperature or increase. I must be careful here because I don't know the way this is set up in this book of yours. It bothers me. But anyway, so apparently when there's a change in temperature, it looks like that. So I'll put it here. Okay, no, let me put it here. I'll show you now what it looks like. In fact, it looks like this. Yeah, because this thing is the way they set it up. It's a bit, yeah. So it should be an increase in temperature. So it looks like this. It looks nearly the same. I think I took the wrong. Yeah, but there's an increase and decrease in temperature. Yeah, so this is an increase in temperature. I think I took the wrong one. Okay, you must just be careful. So this one, yeah, it looks like this. There we go. So that's for the one when the temperature increases, which typically happens. But there is a condition where it decreases. But do not worry about that now. Once you understand the increase, the decrease is also easy. And then again, when they're asking for the final length, like we just did in the last question, the one with the length AB, the junction, you have to use this formula. So this is what's important here. Okay. And alpha 1 is I believe the material that becomes I'm gonna just be sure. 1 is the one that is shorter. So it's the smaller alpha. So I will just get that right here. You must just be very careful on what we do. Yeah. It's just the way they're putting these notations, it bothers me. But just reading off the text here. I'll show you right now. So we just have to make sure we get this part right. What is alpha 1? What is alpha 2? But this will tell you. You understand right now. But anyway, let me just do the example and I'll show you. Okay, so what we have here is, and now again for this question, right? We're gonna do the temperature part first, and then we're gonna do the mechanical part in module 2, and then we're gonna add the two stresses. So I hope you're following the trend. So here we have a compound bar, we have a steel rod, right? And a copper tube. So on the outside, we have a copper tube, okay? And on the inside, we have a steel rod going inside here. So a rod, okay? So this guy, okay, just bear with me. That's a steel, and that's copper. Okay, so let's begin. So they have the same length. The length is, doesn't matter, it's 80 centimeters, but we don't really need the length. We only need the length at the, if they're asking for the, you know, the increase in length. So that's an 800 more setup. And for 3.1, we're experiencing a change in temperature. So the first thing we do, again with this question, we say F1, if steel equals F, what is it? F copper. So F steel, all right? F steel is going to be stress of steel times its area. Now its area is giving as 2.5 times centimeter times 10 to the 2. I don't know if you guys can do that, but that should be 2.5 times 10 to the negative 4 millimeters. That's conversions, right? And then we have your copper 735. Lucky enough to work it out. So 735 times 10 to the negative 6. I'll just give you a quick hint. If you have centimeter squared, it's times 10 to the negative 4. If you have millimeter squared, it's times 10 to the negative 6 to get it in meters. Okay. Yeah. Okay. Sorry about that. So can I just get my stress and my copper ratio? This is always the first step for both parallel and series in temperature. Okay. Let's quickly get that. I think we're just going to have enough time for these two questions. Takes a bit, yeah. Smila, are you with us? Excuse me. And this is coming out the December paper of last year.
Is 294 times 10 to the power 3.
Okay. So what is the ratio?
I'm getting 210.
No, man, the ratio can't be that high, man. It must be 0.12 or something, man.
He just took it the other way, but
Oh.
Oh yeah, but it's 2, I don't know if it's right, 2,94.
Which side? The side.
That will be,
Yes,
just check. Yes, sir.
Yeah, like this. Okay.
Yes,
Oh, I
sir.
see. That's fine, right? So guys, now, once we have this set up, like I said to you, we must revert back into this formula over here. Okay? This one over here. You see here? This is the one we're going to be using now. Okay? So it's going to be alpha 1, right? Minus alpha 2, change in temperature. Okay? And that's going to equal to your stress of your steel L. We don't need L, remember, because it's all the same length. It divides out of steel. Plus we have stress of brass over the elastic moduli of, what is this guy, of brass. Okay, so we don't have L over here because all the lengths divide out. It seems. Okay, so now how this setup works, right? You normally want to put the one with a higher value here, okay? And I don't like to say it like that, but in this
Yeah.
case, I just for the sake of ease, so the one with the higher coefficient of expansion, you'll put over here. It's 18. There's an actual understanding why it's all like this, by the way. And I'll try to explain it at the end. That's 18. And then the smaller one was steel, which is 12, right? Okay, yeah. It's just, you don't just, some people like this. This is telling you that this guy is increasing in length and this guy is actually decreasing in length. So that this is what these things mean. They're not just, but let's anyway. It's going up by a temperature change of, it's
80.
raised from 30 to 80. Can you see it's initially at 30 degrees, right? So it's raised, then raised by 80, sorry. Okay, it's raised by 80.
It's raised by 80, I want to say.
Yeah, good. Because the thing is, if we say the raised to 80, that means there's a temperature difference of 50. So you must be careful with the wording there. That's a trick question. So it's raised by 80. Okay. So if it says raised to 80, there's actually a difference in temperature of 50 degrees, but this is raised by 80. Okay. So we're actually now at 110 degrees. So now what you need to do again is put this ratio in over here. Okay. So this guy is going to be stress of copper, 2.94. Divided by my elastic modular, I'm hoping it's 200, not 210. Yeah, it's 210. Look at that. 210 and 100. Okay, 210 gigapascals. And then we're going to add brass. Oh, sorry. Why am I so, this? Is it copper or brass? It's copper, man. Copper. Nearly the same thing, right? Is it? Yeah. Copper, zinc, brass. Just clean him up. And over here it's 100. So all you must do now is solve for the stress of copper. Let's see what you get. So again, with this formula, always put a higher coefficient of expansion over here. Right? It's not because it's like that, it means something. It means that the copper is actually increasing in it. I'll start to explain it now. Okay. So let's quickly get the stress in copper. I sometimes feel like I'm on a talk show. We have to rush, like rush the stuff that I know. Like I have to be quick. Okay. Let me just do this here. So the copper's on the outside, so the copper's growing faster, right? Okay.
I get
Something's-
137.5 MPa.
The stress. Let me just verify that. Are you sure about that? I'm seeing different answers here.
It's understood, but let's see. I get 20.
Yeah, it's supposed to be clean 20. Yeah, but it's 20, definitely. 20 megapascals. Yep. So what is the sense there, man? This is what I'm asking. What is the sense there? Compressive or negative? Let's see where the trick comes. Let's see where the trick comes in for this stuff. Yeah. Okay. Let's see where the trick comes in. I'll put my copper red. Keep the steel white. So I'm gonna make my fix in here. I believe that they fixed. But what is my nature? That the nature of stress, sorry, that's what they call it here. Yeah, they're both fixed. Both fixed, very important, right? They're confined. Okay.
I used to some minus.
Okay, anyway, let's find the steel quickly. Time is catching to us. What is my steel? What is my steel?
Oh, sorry, sir.
Yeah, just give me my steel.
58.8.
58.8, right? Though, here we go. So that means if this keeps on increasing and if this reaches its UTS, this will break faster. But what are my senses?
The way I remembered it, but I don't know the reason, right? This is how I remembered it from practicing. I normally know the one with the highest coefficient of linear expansion will be
Expansion.
compressive, and it will be a minus, obviously. It will be a negative.
Yes. So this is what's happening here. Long story short. Remember, this thing was fixed most, right? It's exactly like the series arrangement over here, right? So when this increases, like, right, the whole is going to compress this one. It's going to want to compress this length, basically, right? That's what we did before. So this is compressed. But now the thing is, as this is pushing, this doesn't actually, this part here doesn't actually extend to the hole, or it's actually increasing while this is increasing. So this sense is tensile. So long story short, as Louis is saying, the one with the higher coefficient of expansion, right? The alpha 1 will come over here. It will experience a compressive stress, right? But and the steel part, right, will experience a tensile. This is the main thing you must know. Okay. I'll try to explain it after I'm done with the whole thing. What's exactly happening here. But we just keep it like, unless Louis has a quick explanation of what's happening here.
No.
Sorry, sir, may I
Yeah.
ask something?
Yes,
I
again.
think there was something that I want to ask. There was something that
Yes.
when I was browsing, there was something with 20% when it's below 20% is brittle or ductile. If you can explain me about that, man, the material when it's above 20% is brittle or
Okay.
ductile. I'm not
It's not related
remembering.
to it's not related to
Oh,
this, no? So can I answer that question afterwards, no? Is it fine?
okay, no problem.
Yeah, okay. So remember this, right? Just as for now, there's an explanation for this. And it's to do with as the one increases, you know, the one with the higher, it's gonna essentially put a compressor force, and the other one will be tensile. It's rough to explain quickly, but I'll try to do it afterwards. Anyway, so guys, this is the first part. This is the temperature part. What is key? Get the sensors right. No? Compressive, tensile, right? Don't confuse the two. The time in this
So just a
changes.
question.
Yes.
How come you guys only use the 80 but don't add the 30 to the 80 to make it
30 to the-
110? For
Oh,
the
the
increase was
temperature.
what?
It's
Yeah, it was
raised by
Mr. 30.
80. So the change is 30. So we're going from
Okay.
30 plus 80. If it says raised to 80, you understand? So it's raised by 30. So we actually increase it to 110 degrees. But if the question said raised to 80, we're only having a temperature difference of 50. Are you with me?
Yes.
Yes. So it's an English thing, man. Okay, so now, yeah, when we come to this setup, so now we've done the temperature, right? Temperature came in here, got hot, things happen, right? We got stresses in the material. Stress here, and stress here. Now what we're doing, they say they're putting on a 40 kilonewton load going that way, right? Tensile load. We're taking the same assembly. Now you're putting a 40 kilogram load. Now we're going back to module 2. See, now we're done in module 3, right? So who can remind me my formulas for parallel? Quickly. The total force must equal module 2, gents, colleagues,
F1
students.
plus F2.
Yeah,
F1 plus F2, yeah.
yes, the F steel plus F copper. Can you
Yeah.
see how this is different from that? You see there? Temperature is always the setup. The same force is producing these changes, you see? And then the same thing is the total change in length is equal to the, you know what I mean?
Yes. Equal to one another.
This one. Yes. Oh, let me call it X here, no? X total is equal to X steel equals to X, what is this? X copper. So now we have two choices again. We can either do the stress story or we can do the force story, right? So let's just keep on with the stress one. So now we must find ratios of stresses and then plug it back into the force formula. Okay. So we're going to use this one. So we know that this is going to be this is equal to that. So this is stress steel. Length is the same. We can actually cancel out the length. So I'll cancel again now. That's E steel. And we have stress, what's this again? Copper, L over E copper. And again, the reason why we can cancel the lengths out is because they are the same length, right? So let's find my two ratios here. And again, I'm saying, colleagues, remember, this is the mechanical part now, right? We've passed the temperature part. So give me the ratios quickly. Should be easy. 2.1, I think. 210 divided by 100.
2.1
Yes,
is
it's 2.1.
Yeah. Right, though. Once we have this guy, we take this guy, we plug it into over there. So now we know that F total is equal to F steel plus F copper. Our total load was, what was it again? A load of 40 kilonewton, right? This is stress of steel. Each respective area was the same area as before. It's 2.5 times 10 to the negative 4, all right? Plus the stress of copper. And stress that the area of copper was 735 times 10 to the negative 6. And obviously, what do we do now? We take this guy, we throw him in there, and then we solve for copper. Okay, let's do it quickly. Nearly at the end now. My battery has, I think, 10 minutes, just 10 minutes left. Okay. Let me find the stress quickly. Quickly get that.
I got 50.794.
Colleagues, I didn't hear you.
51, yeah.
I got
41.
31,746. I don't know. What did you
Okay.
say, Hussein?
Yeah,
I got 50.79.
I think it's 31. You're out somewhere. Remember, we must substitute this guy, the 2.1 here, no? This must come in here. So, colleagues, we got the 31.746, but what force did we put here? What force is this? The nature of the force or the sense? You was a?
What did you say? Tensile.
No, tensile force. So therefore the stress must be tensile. In fact, for both it's going to be tensile because it's the same force. So we times this guy by 2.1. Should we get what? 60 odd?
Yeah. 66,67.
Here we go. 66,67. And again, tensile, right?
Mm.
Okay. I hope you're all there. Now we come to the big boy stuff that everyone's crying about, the resultant stresses. Very simple. All we're doing is adding stresses, right? So now we're going to say resultant stress of steel. We go first to the temperature side. Temperature, what did we get? Oh, we got a 5.8 megapascal. Tensile, that must be a plus, right? So we put the 58.8 positive, right? Because it's tensile. Am I clear? Then we look at the, well, what is this? We look at the mechanical side, right? Where the mechanical load was. It was the 66.6, right? It's also tensile, right? That's why it's a plus. Or no, we add them up. So what is the resultant stress? So the 58.8 plus 66.67.
125,47.
125,47. MPa
That's correct.
tensile. Can you see? Simple. We do the resultant for the copper, right? So now remember, our copper extended faster, but it was a compressive stress, so it's negative, right? So that's negative 20. Okay, this is the correct notation. Are you happy? We go back to the mechanical load, and we saw the copper experience a tensile force now, so that's a plus. It's a plus 31.746. So this was a compressive, that was a tensile, and now we just add them up. What do we get? It's quite obvious there, right?
11,746.
Yeah. And there you go, students. Welcome to N5. 746 megapascals. But what is the sense? Positive, is it tensile or what is it? Tensile or compressive? Compressive, exactly. It's compressive. There we go. So stepping back, I mean, look how interesting this is. Look how beautiful it is, right? Just look. You have an assembly, you put on temperature, things happen. You put on mechanical loading, things happen. But look, this is the actual stress each material is experiencing. But still, the steel will break before the copper. No. Yes, the steel carries most of the weight. Just like in teamwork in companies where we work at. Some is carrying more weight than the others. It's funny. But anyway, this is it, students. This is the resultant part. And
So
most of the questions. Sorry, go for it, Chief.
No,
Let's
so
discuss.
I want to ask there, when you worked out the stress, not that the resultant at the bottom, when you still worked it out the stress due to temperature, if you
Yes.
they were compressive, if you added a negative in front of the 20, will the answer be wrong or right? Because
That's
I see
correct.
the book put a negative in front of as soon as it's compressive, but I see
Yes.
obviously some memos don't put it negative now.
No, negative is compressive, 100%.
Okay, so it won't make
Yeah.
it won't make a difference.
It's known as compressive. It's like when you're computing a stress value, a negative means a compressive value. Clean. You understand? And a positive means a tension value. Because remember, compressing decreases the length anyway.
Yes.
That's the idea. You know what I'm saying to you? But I saw some N5 textbooks where the guy just decided to make his own stuff up, and I just laughed. But the third book is alright. Is there any questions with this before I end off with Somila's question? Guys that open your minds, the guys who have done this before, have it made some kind of impact? I hope so. Some people say this is difficult, but I'm like, I don't see it. But thanks, Mangaliso. Thanks for saying. Very important to understand the difference between the two. All right. So Mila, to answer to your question, so brittle, ductile, right? This is module 1, I believe. So a ductile graph looks like this. We apply a load, and there's a long extension before it breaks, right? A brittle graph, you apply a load, it breaks one time. Okay. So what we typically deem as a ductile is when this is equal to and greater than 20% percentage elongation. Again, this is an agreed upon value, right? We come together and we say, yeah, we're going to call this ductile. This is very negotiable, right? So it's not absolute. This guy is less than 20%, and we call 20% percentage elongation, then we call it brittle. What it basically means is that if a material is ductile, before it breaks, it extends a bit, we can scream before it breaks, and then it breaks. Brittle means as soon as it reaches its maximum load, there's no time for screaming, it breaks. That's the difference. In the most layman's term, I can say. Students, we've come to the end of our session. Is there any other questions on module 3? If there is time next time, which I doubt, I can do another example in module 3 if you guys require, but I want to move on to module 4. You know, our time is very short.
Maybe a bolt in a nut one.
100%. Yeah, now you're talking to me. That's what I want to hear. So Louis, maybe you can pose a question for next week, Wednesday, and I can start with the bolt and the nut, then I can continue with chapter 4. No? Is that fine?
No problem.
Yeah. And again with the bolt and nut, remember the bolt and nut, there's going to be the temperature side, which works basically the same, right? And there's also going to be the mechanical side, which I taught you the last time. It's the same setup. You should be able to do it, but we're going to do the bolt and nut. Just put it for next week, Wednesday. So I can do that one first. Okay, my colleagues, it was a fun session. Hope you guys learned something, and yeah, I will see you next week. Same time, same place. You know the drill. Cheers. Thanks, Louis. Thanks, Mangaliso. Thanks, Mila. Thanks, gents. Okay. There we go. Stop sharing. Thanks, Brandon. Then I post the recording.